So good afternoon. Thank you for coming. Today we have Olivier. He's a PhD student in Lyon, and in the last few months he was here with us, study with Martin mainly, temperature, physical temperature coefficient of silicon and photovoltaics. So welcome Olivier, that will summarize his findings from the last few months.
Thank you so much, Z, for the introduction. So yeah, I had the great opportunity to come here at UNSW to study under the supervision of Professor Green for 6 months, and it's been a real pleasure. And originally my lab is not a photovoltaic lab, but more of a thermal engineering lab, so that explains maybe why I'm going to talk about physics of the thermal behavior of PV cells. So as I'm sure all of you are aware of, the efficiency of PV devices is negatively affected by the temperature of the cell. As you can see on this graph right here, the efficiency of the different PV cell technologies goes down as the temperature increases, and it does so at different rates for the different technologies. The question we're going to try to answer here are why is fundamentally the PV devices affected by temperature, and what are the parameters involved. So to do that, we'll first have a look at the fundamental losses in the photovoltaic conversion process. We'll talk about the detailed balance principle as introduced by Shockley and Quester in 1961. And we'll also have a look at the thermodynamical approach and look at the energy and entropy balance of the cell. So once those fundamental losses will have been understood, we'll talk about their dependence on temperature and investigate the temperature coefficients of ideal cells, and then we'll add to the picture the additional losses that happen in real device to understand better the temperature coefficient of commercial cells and what can give the temperature sensitivity of different technologies. And in the end, we'll just present a thermal engineering view on what we could expect from photovoltaic in the field with given temperature conditions. So the detailed balance principle is based on a really simple fact that for an equilibrium to exist, there has to be as many transitions from a ground state to the excited state, or from the excited state to the ground state. Here, if we consider our semiconductor with the valence band and the conduction band being separated by an energy gap, the electrons can go from the valence band to the conduction band when they're excited by the photons. And then they can go from the conduction band to the valence band by recombination, the inverse process. And they have another option, is to go like through some external circuit and where their energy will be used and we will get electricity from them. So the idea of Shockley and Quester was to make a few assumptions to be able to relate the population of photons to the population of our excited electrons. So they say, yeah, every photons that will excite only one electron, and all the recombinations that happen in our device are radiative. That means every recombination generates a photon. So that brings us some ultimate limit, because this is the inverse process and we will never be able to get rid of it. And if we say that and look at the whole cell, then it's obvious that if there's less photons that are emitted than photons that are absorbed, it means that for an equilibrium to exist, there is a current flowing from the conduction band to the valence band through an external circuit. So this current is equal to the difference between the absorbed photons and the emitted photons. And to get a photon flux, we can make use of the generalized Planck's equation that relates the number of photons per energy interval, E. We see appearing there the solid angle. So here we are considering that the cell is absorbing photons from the cell in a given solid angle, and it's emitting in a different solid angle as a regular cell. So we'll see that we can play on that afterwards. And so this equation is exactly like the Planck equation, but there's one additional term here, mu, and mu is the chemical potential of the radiation. And it can be shown that it is equal to the chemical potential of our electronal pairs. And if we assume that there's a perfect charge transport, then we can say that mu equal QV. Also, we integrate from the band gap to infinity because Shockley-Quester made the assumption that we have a single gap absorber. So every photons that have an energy above the gap is absorbed in our cell, and none of the photons that don't have enough energy. So this tells us that the electrical power that can be drawn from our cell is equal to the electrical charge times the difference between the absorbed and the emitted photons times the voltage at the contact of the cell. And we see from that equation that the flux of photon that is emitted toward the ambient will depend on the voltage, because the voltage appears here with the chemical potential of the radiation. We can also have a look at, we can derive the same limiting efficiency looking at the with a thermodynamical argument. So photovoltaic is about converting radiative energy from the sun into electricity. And the proportion of electricity, of useful work we can get from our incoming solar radiation depends on the free energy that is contained within it. And this free energy is related to the amount of entropy that is contained within it. So if we consider here in orange the gas of our excited electron-hole pairs, they have a free energy that is an energy that can be extracted to produce work. And this free energy is equal to their internal energy minus a term that is the product of their entropy and the temperature of the cell. And this corresponds to some disordered energy that will ultimately be converted into heat and will not be, so we won't be able to get that energy as useful work. So we can do as we did before in the Shockley-Queisser approach and look at only what goes in and out of our system. And to get the entropy flux, we'll make use of the irreversible thermodynamics that relates the entropy flux with the energy fluxes and the free energy fluxes, where here we see the amount of free energy contained in our electron-hole gas divided by the temperature of our system. So the condition for equilibrium is written in those two equations. There's to be as many energy entering the cell as energy leaving the cell. And the entropy that leaves the cell has to be equal to the entropy that comes into the cell plus the amount of entropy that may be eventually generated within our cell. So this, if we sum those two equations, we understand that the output power we can get from our cell is equal to the chemical potential of the radiation times the difference between the number of absorbed and emitted photons again, minus a term that is there because there could be additional entropy generation within our cell. But if we do the same assumption as we did in the Shockley-Queisser approach, we show that we are in the case where we assume that there is no extra generation of entropy, and so the chemical potential of our electron-hole pair equal the Q times V being the voltage at the contact of our cell. So with that thermodynamical approach, we get the very same results. The electrical power that can be derived ideally from the cell is equal to the voltage at the contact of the cell times the difference between the absorbed and emitted photons. So we find that again here, and so it tells us that the electrical power that can be drawn is a function of the gap of the cell, of the temperature of the sun, of the solid angle of absorption, but also of the solid angle of emission of our photons, and of the temperature of the cell and the voltage. So in a given set of in a given configuration, when we assume that the sun and the cell temperature and the solid angles remain constant, the maximum power we can draw out of our cell is found by solving those two equations, this set of equations. And here we'll show that if we use a Boltzmann approximation and neglect the -1 term in that generalized Planck's equation, it's possible to find an analytical solution of equation 1. And this equation is really interesting because it relates the optimal operating voltage, that is the voltage where we can extract maximum work from our cell, to the gap of the cell. And we see appearing here the Carnot efficiency, and there an additional term that is due to the entropy generation because of the angle mismatch between the absorbed and emitted photons. And yeah, we precise here that this equation is only correct when the gap is also maximum, because we have not solved equation 2 right here, but we'll show afterwards that it's quite a good approximation and it gives us a good insight of what are the fundamental losses. And so using this analytical solution, it's possible to relate the maximum power that can be drawn from our cell to the input power and a different number of losses. So we see here those losses depicted as the function of the band gap of the cell. So the blue losses that we find first is due to the fact that a solar cell is like an Carnot engine, in the fact that it cannot get more work. The maximum amount of work that it can get is limited by the difference of the temperature of the sun and the temperature of the cell. In orange, we find a loss that is due to the fact that all the radiation emitted by our cell is lost to the conversion process. And in a PV system, in a regular PV system, the photons are emitted back toward the ambient, and we're not getting any energy from them. And in the dark blue, we have the loss that is due to the fact that normal cells emit in even more directions than they're absorbing photons from the sun, so the balance is even more shifted. And the red and the purple area shows that the main losses we have in the PV conversion process is due to the fact that the solar spectrum is really broad, and we're using a single gap absorber to collect that solar spectrum. So there's a lot of photons that don't have enough energy in red, and there's the photons that have the energy can only give the gap, and all the energy they have in addition to the gap will be lost. So we'll show, of course, all those different losses can be reduced using different approaches. We can try to reduce the angle mismatch loss by limiting the angle of emission of our cell, or concentrating the light so that the angle of absorption is increased. We can try to reduce the spectral mismatch between the solar spectrum and the cell by using multi-junctions, splitting, putting different cells with different band gap, so fitting better the wide solar spectrum, or spectral splitting. We can try to make use of the photons that don't have enough energy using up conversion or impurity photovoltaics. And there's also options to make use of the extra energy of the photons, like hot-carrier solar cells, down conversion, multiple excitant generation. And other ideas like solar TPV or thermophotonics, whose design are so different that will actually, all those different losses will change. But let's look at those losses at a given gap. We take, for example, the gap of silicon here, and show those same losses, but on a more familiar picture on the band diagram. So here is a band diagram of an ideal silicon cell at the maximum power point. And so what we can find the losses depicted on this graph. Here is the incident energy. The photons who don't have enough energy to be absorbed will eventually go through the cell and won't be absorbed. Those were absorbed give away their extra energy here quickly to the photons by a process called thermalization. And when we shine light upon the cell, we put the cell into disequilibrium. So of course, those excited electrons will have a limited lifetime. So some of them will recombine, and that's where we find our emission losses. Every recombination will emit a photons, and those photons will be lost to the energy conversion. And then what's interesting is that we find our Carnot and Engels mismatch loss here at the junction, and those losses are there to give us the driving force to separate our excited electrons from our excited holes. It's possible to also relate those losses to the IV curve of an ideal silicon cell. So here what we see is the accumulated photon flux density as a function of the photon energy, and it's quite similar to the current density that we can get from our cell as a function of the cell voltage. So if we take a gap right here, like the gap of silicon, we see that there is that number of photons that have enough energy to be absorbed. All this area here represent the energy of the photons that are not enough, that don't have enough energy to be absorbed. And here in purple, we find the energy of the photons that are absorbed, all the energy that is above the gap, and it's lost in the thermalization process. So it leaves us with this square right here, but we cannot extract all that energy because, as we have said before, the emission from our cell is dependent upon the voltage. So when we increase the voltage of our cell, the emission loss here depicted in orange will gradually increase. So there is a maximum power point, a point where we can extract the maximum energy. And this point is given by the analytical solution we have found. So the optimal voltage is related to the gap by the Carnot efficiency and some Engels mismatch loss. And the optimal current is differ from the short circuit current by the number of photons that are re-emitted to the ambient. So now we've talked about the fundamental losses in the photovoltaic conversion. Let's come back to our main topic and talk about the dependencies of these losses with temperature. So the emission rates obviously increase when the temperature increases. So the angle mismatch loss will obviously increase as well because there will be more photons emitted in every direction. And as the cell temperature of the cell increases, the difference of temperature between the cell and the cell decrease, so the current loss will increase as well. Here we see those different losses depicted at 300K and at 450K, and we can see the Carnot, the angle mismatch, and the emission losses part increasing largely. And we can also look at that at a given gap and see that they are increasing linearly with temperature. And that means that if this loss increase when the temperature increase, it means that the maximum power that we can extract from our cell decrease when the temperature decrease. And this relation between the cell temperature and the maximum power we can extract from our cell is characterized by the temperature coefficient. So the temperature coefficient is defined as the variation of the efficiency with temperature divided by the efficiency at room temperature. And this variation here, we have understood that it's proportional to those different losses. And so the temperature coefficient will be a function of those different losses divided by the output power, because our temperature coefficient is defined as a relative variation. And we plot that on that graph and show that there is a perfect correlation between the temperature coefficient and this ratio here. And that means that from that conclusion, we can understand that if we reduce those losses, then we can improve the temperature sensitivity of our cells. And here's an example of that with the concentration. So here we see again the different fundamental losses in the photovoltaic conversion process at a concentration of 1. And here we have those losses at the maximum concentration. That means the cell sees the sun from every direction. So what we see here is that when we increase the concentration on our cell, then its maximum efficiency will increase. And what we can deduce from what we've seen just before, as its maximum efficiency increase and this angle mismatch loss decrease, then its temperature coefficient will increase, and that's what is depicted on this graph there. At any gap, when we increase the concentration, the temperature coefficient decreases. So minimizing the angle mismatch both improve the efficiency from our devices and improve the temperature coefficient of our devices. And now let's look at the additional losses in real PV devices. So we have shown that the temperature coefficient was the function of the gap. Here we show the analytical and the numerical results, and they're quite close except at low band gap where the Boltzmann approximation becomes erroneous. But we also plot some experimental measurements that we have presented in the first slide, and there's quite a large difference between what we can expect so far and the experimental measurements. And the reason for that is that in real devices there's a lot of additional losses. The biggest one being that most of the recombination are not radiative. There's a lot of non-radiative recombination processes happening. So there can be a Auger recombination where the excited electrons will give its energy to some other excited electrons and then recombine. Shockley-Riddle recombination, there are recombination through defect in the bulk of our silicon, and surface recombinations where the electrons jump from like one defect to another at the surface of the cell. So that's one important thing that will reduce both the current we can extract from our cell, and will also add to the Carnot and Engels mismatch and decrease the maximum voltage we can get from our cell. And we see here like all the voltage losses in our cell, and we see there's also two additional ones that are due to the series resistance, being if the bulk of the material is resistant, then there will be some transport loss, and there could also be some loss at the contact, when the contact is not excellent. And with depiction, we show here a last additional loss, that is a shunt loss. It's when an electron actually is lost because it goes back from the conduction band to the valence band, but it doesn't go through the load. So all its energy is wasted to the conversion process. So once again, we can have a look at that on the IV curve. We plot here a more realistic IV curve, and we see that it differs from the ideal IV curve by the factors we have introduced, by the loss due to non-radiative recombination here in green, the loss due to shunts that will reduce the current we can extract from our cell, and the losses due to series resistance that will further reduce the optimal voltage of our cell. So to try to apprehend what those non-radiative recombinations, what is the impact of those losses on the temperature coefficient, we'll introduce the external radiative efficiency of the cell. So the ERE is defined as the number of photons that are emitted divided by the total number of dark current recombinations. So it's quite similar to the EQE of a LED in that it tells you how many electrons needs to be excited to emit one photon. So if we introduce this term in a classic diode equation, we can get that equation, and once again using Boltzmann approximation, we can get an analytical solution that relates the optimal voltage to the gap. And we see that this equation is exactly like the one we've presented before, but there is another additional term due to non-radiative recombinations. This term here, we can see that it has a temperature dependence. It depends linearly upon the cell temperature, and thus it will have an impact on the temperature coefficient. So to show that, we plot here the different losses for a cell whose ERE is about 10 to the minus 5. That is the ERE you could expect from an average commercial silicon cell. And we plot the different losses with an ERE of 1.5, 10 to the minus 3. That is an ERE of a really good silicon cell. And obviously, what happens is that the efficiency of the device is enhanced when the ERE is lowered. So the quality of the silicon is better, so we can get more electricity out of it. But as we are reducing this loss, we're reducing the ratio once again of the loss that depends upon temperature. So we're once again reducing the temperature coefficient of the cell. So minimizing the non-radiative losses improve the efficiency and improve the temperature coefficient. And that has been noted already some time ago by Green. As the open circuit voltage of silicon solar cells continues to improve, one resulting advantage not widely appreciated is that is reduced temperature sensitivity of device performances. So when the quality of the cell increases, the temperature coefficient of the cell should increase as well. So the temperature coefficient is a function of the ERE. But there is some other thing that we have to consider. The radiative and non-radiative recombination processes have different temperature and voltage dependencies. That means that as the ERE is equal to the fraction of those mechanisms, it will be a function of temperature itself. So the temperature coefficient could be a function of the temperature. So we give an example here. It's using the Shockley-Redel recombination theory, and we take two different trap energies. And we see that the field line here correspond to the gap that is in the middle, the energy that was the defect whose energy is in the middle of the gap, and of course it's more damaging for the cell, so its efficiency is lower and its temperature coefficient is lower. But what's interesting in that graph is that the temperature coefficient of those two defects is really different. Here the temperature coefficient will not change as the temperature increase, and for this kind of defect, the temperature coefficient will be enhanced quite largely when the temperature increases, because those two have two different temperature dependencies. There's also other things that could complicate the analysis. There could be series and chain losses that are a function of temperature, and they can have quite an important impact on the temperature coefficient, as is particularly obvious for experimental devices whose series and chain resistance are quite important. They can have temperature coefficient hard to explain. And there's also something that is material dependent. The band gap of every semiconductors varies with temperature. Most of the semiconductors band gap decrease when the temperature of the cell increase, as we can see on this graph here. They're moving slightly toward lower band gap when the temperature of the cell increase. And except one particular semiconductor that is a perovskite compound, and it's pretty interesting to note that its variation of band gap with temperature is positive, and that means that it could be really interesting in terms of temperature coefficient, because we have seen that the optimal gap for converting the incident radiation increase when the cell temperature increase. We see here that the maximum is shifted to a larger value, and that this perovskite compound happened to have exactly the good variation of gap with temperature to follow this trend. So here is plotted the temperature coefficient of those different semiconductors, and we see that those that were on the left side of the optimum as temperature coefficient that are worse than predicted if you don't take into consideration the variation of band gap with temperature. And those with temperature whose band gap were larger than the optimum on our previous slide as temperature coefficient that are actually better than expected. And we plot here the fictional curves. The green and the orange curve are here to show that there is a strong influence of the spectrum on the temperature coefficient, because if the gap changes with temperature, it means that the maximum number of photons that can be collected also change with temperature, and this depends on the gap. And we see here some strong variations for a given variation. But of course, every semiconductor has its own variation of gap with temperature, so it's hard to predict that in a general way. So, and now we'll talk about the intrinsic temperature coefficient of silicon cells, because it's not enough to know the temperature variation of the band gap. There are also other processes that makes the limiting efficiency of crystalline silicon cell different from the Shockley-Queisel limits. Those differences are written right there. Once there is Auger recombination, that is an intrinsic process that we cannot get rid of. In any case, it's not as Shockley-Queisel recombinations that can be reduced by reducing the defect. Auger recombination is some intrinsic processes. And then there's the fact that in silicon there will be free carrier absorption, so we will not be able to absorb all the photons below the gap and all the photons that have energy above the gap and none of those below. So we have a realistic considering a realistic absorbance here, and so it's explain why the limiting efficiency of crystalline device is lower than what the Shockley-Queisel limit for the same band gap. And from the state-of-the-art parameters and considering carefully their temperature dependence, we've derived some intrinsic value for the temperature coefficient of crystalline silicon solar cells that you can see right here. Of course, it's not a minimum because of the other effects we have talked previously, like for example, the contact losses could have temperature dependencies, could get better when temperature increases and leads to lower temperature coefficient than that. But as silicon cells improve toward their limiting efficiency, then their temperature sensitivity is expected to converge towards this value. Now to conclude, I will just give a thermal engineering point of view on PV performances. So we have talked about the dependencies of the maximum output power on the cell, the dependencies on the output power on the cell temperature. and we have shown that is related by the temperature coefficient. But if we, but now we'll look also at what gives us the cell temperature, what drives the cell temperature. So on this graph we have added a few terms. The Q is the heat source within the cell, and this heat source is in fact can be calculated easily from these different losses. All the energy that is absorbed within the cell and that is not converted into electricity is eventually given to the photons and act as an heat source within our cell. So the heat source can be easily calculated from that graph. And now if we consider some thermal outdoor conditions, let's say that the external temperature is 300 Kelvin and the heat transfer coefficient between the cell and the outdoor is 10 watt per square meter per Kelvin. It's more or less what you could expect from a building integrated photovoltaics. And let's have a look at the maximum efficiency if you don't take into account the thermal problem at all. So if you calculate the maximum efficiency at 300 K, it gives you this green line right here. But now if you take into account that the cell will heat over the ambient temperature because of the heat source within it and the heat transfer coefficient, then you get something that looks like that, the red curve here. So it's important to consider the outdoor conditions to be able to know. For example, without considering them, you will say that silicon is better, will give a better efficiency here. But if you consider that, then you see that silicon will probably operate at a larger temperature. And as its temperature coefficient is larger than CDT, then those two aspects will lead to silicon operating at lower efficiency in real conditions. And as it is true for ideal cells, it's even more true for commercial cells. Now we're doing the same thing, but with a different ERE. So the heat source is increased because there's all those non-radiative recombination processes that increase the heat source. And we have seen also that when the external radiative efficiency is worse, then the temperature coefficient is worse. So the impact of considering the all thermal problem will be even larger. There's an even larger shift between the green and the red curve. And in this condition, if we consider non-ideal cells, then it will be more interesting to go to a larger gap. So in conclusion, we have shown that reducing angles mismatch and non-radiative losses will improve the efficiency of the cell, but also will improve the temperature coefficient of the cells. We have seen that at one cent, the temperature coefficient is mainly a function of the cell band gap and its quality, related to its external radiative efficiency. And we've shown that the temperature coefficient is also a function of a lot of other parameters, such as the variation of this ERE with temperature and the variation of the contact loss and chance loss with temperature. So we'll try in the future to investigate the impact of these other parameters to be able to predict the temperature coefficient of different technologies of cells that can have different contact losses and different shunt path. And we have derived an intrinsic temperature coefficient of crystalline silicon that is equal to minus 2,380 ppm per Kelvin. And we have just introduced a thermal engineering point of view on what kind of efficiency you can expect from a cell in a given thermal conditions. And we'll try to assess different PV strategy using this thermal approach. And I thank you for your attention. I'll be glad to have any questions if you have some. Yeah.
What spectrum did you use in most of the graphs, like over the bandgap?
So for the first graph, where we were using the analytical approach, we're using a black body at 5,800 K, and then afterwards we have used the AM 1.5 spectrum to show the impact of the spectrum and the temperature coefficient. Yes.
In slide number 11, can you please explain how you correlated the angle mismatch loss with the band, the energy band?
I'm not in that slide.
Level.
Oh yeah. Oh, so yeah, this on this slide we understand that those losses that are voltage losses happen at the p-n junction of the cell, at the junction in the p-n junction. I'm not sure if I exactly understood your question.
Yeah, I was asking that angle mismatch plus Carnot losses.
Yes.
How you attributed to that losses to this junction law.
Oh, because in an ideal PV cell, the band will be flat, and the only place where you have a voltage drop within your cell is at the junction, and the fact that you cannot reduce you cannot reduce this more is that you need some driving force to drive your current flowing through the cell, and if you don't have that amount of voltage drop, then you will have a larger emission, and you will be past the maximum power point. Does that make sense? Or yeah, sure. We can discuss that afterwards. Yes.
Have you had a look at multi-junction cells? And I was just wondering how the different band gaps that like a triple junction cell also, for example, has. How does that translate into the temperature dependence, especially like each of the single cells? How do they contribute to the overall temperature dependence?
For real multi-junction cell, it's really interesting because if they're connected in series, then for example, the variation of current with temperature will be given by the variation of the limiting cell. And then all the different variation of voltage with temperature will just sum up because they are connected in series.
So the cell with the lowest band gap would be strong consideration to choose that as large as possible.
Like all the band gaps will have an impact on the overall temperature coefficient. The band gap, like the choice of all the band gaps in the multi-junction cell.
But because the lowest band gap would be the most sensitive to temperature,
yes.
I assume that it would be good to choose a larger band gap for the lowest one to have less sensitivity.
Yes, but then it's a balance between the temperature coefficient and the amount of photons you can collect. But it's true. Yeah, thanks. I just did an ideal calculations if you're considering an ideal multi-junctions, and the quite surprising result was as you stack the cells together, the temperature coefficient of the total doesn't change because the temperature coefficient we've seen was proportional to the ratio of those different losses on the efficiency. So you're adding some losses because you're adding different cells, but you're also increasing the maximum efficiency of your cell, so the relative variation with temperature doesn't change when you add some junctions, in the ideal case. Yeah.
Does it also hold true if it is less than room temperature? So will your expressions or your relationship hold true?
Yes, it doesn't matter what's the temperature. The only thing is, the temperature coefficient is defined as a fraction of in comparison to the efficiency at room temperature, but it doesn't change anything for the rest of it. Yes.
The Alta devices cells meant to be really good, like radiatively efficiency-wise. Did you have a look at that one? The temperature coefficients of it, particularly?
Actually, no. What I would like to do now is try to measure some external radiative efficiency and measure temperature coefficients and see how good this this expression is. Can you relate the temperature coefficient to the external radiative efficiency? But there will be, as I said, other processes that may make the difference between the simple correlation of the quality of the cell to the temperature coefficient. like if there's additional contact losses that have different temperature dependence, then it's not that easy to, you cannot only take the ERE and get a temperature coefficient.
More questions?
Similar question. Actually, you show the temperature coefficient can, that the energy trap energy can change the temperature coefficient.
Yes.
You think it's practical to use a temperature coefficient to actually derive the trap energy? Is it possible to develop such?
Yeah, I think I understand. Actually, that's something I would like to do also as well, to try. It's to see if different known defects leads to different temperature coefficient. Was it the question? If it's possible to know from the defect the temperature coefficient you can expect? Or, yeah, I don't know. It has never been done, but it's possible that it can be doable.
More questions? So let's thank again